This episode is sponsored by Unpacked's new podcast, Homeland, 10 Stories, 1 Israel. All right, picture this, guys. Israel, 2022. A crowded bus breaks down on the side of a desert highway. Who's sitting next to you, and what secret will they reveal? The newest podcast from Unpacked, Homeland, 10 Stories, 1 Israel, will keep you on the edge of your seat as each passenger's story unfolds. Meet the Russian immigrant who escaped the Soviet Union and the Jerusalem native whose family traces back over 400 years. Each week, you'll meet a new character whose story will take you for a ride. So get on the bus, grab a window seat, and settle in for Homeland, 10 Stories, 1 Israel, wherever you get your podcasts. Hey guys, before we get into the episode, we just want to talk a bit about how you can support the show.
That's right. We recently opened a brand new Patreon account, and this is your opportunity to help and support the podcast.
Yeah, absolutely. We have a tier for every pocket, so whatever you can spare, you can help us out. And if you can't spare, we also appreciate. Keep listening, keep tuning in. But if you have if you got a few shekels lying around, you might throw them our way. We really appreciate it. It would help us keep, doing what we're doing every week and putting out content.
And you'll get amazing perks, amazing prices and bonuses. So if you can spare it, go to patreon.com/2njb. Every sum helps, and you can support the show. So thank you so much, guys.
Thank you. What would you do if you had $2.5 million to invest in scientific research? Would you search for a cure for Alzheimer's, cancer, MS? Would you try to send the first man to Mars? Or would you attempt to create the perfect TikTok video? These are the questions that faced Professor Ido Kaminer from the Technion. Well, maybe not the last one, but Professor Kaminer applied for the prestigious Polymath Award, given each year by Eric Schmidt, former CEO of Google. The rules are simple. Submit a research proposal in a field that you've never explored. In other words, the applicants are requested to leave their comfort zones, think outside of the box, and come up with an innovative idea that's worth the money, $2.5 million. Professor Kaminer was recently notified that he was awarded the prize. Now he faces probably the greatest challenge of his career, trying to explain to us simpletons what in the world his research is about. Professor Ido Kaminer is a physics professor. He studies quantum mechanics, and he's the first Israeli to have gotten awarded the Adolph Lomb medal, which is awarded since 1940 to a person who has made a noteworthy contribution to optics at an early age. It is an honor to be joined today by Professor Ido Kaminer. Thank you so much for joining.
Hello, from Haifa.
Hi, what's up?
You came all the way from Haifa today.
Yeah.
To explain to us something that we're not going to understand.
No, probably not.
Going to Mars is okay. I would have done that if $2.5 million is a little bit of too
it's
little
not enough.
for that.
Yeah. Elon is on the job.
You can barely get off the ground with $2.5 million.
Yeah, exactly. That's not the scale that you need. But that's a worthy goal.
Yeah, but the perfect TikTok video. I mean, their algorithm's pretty tough to beat. So if you could come up with that, I think that would be pretty breakthrough.
I guess it's a good challenge, but I don't know how long-term valuable.
He's a boomer. He'll fail.
He doesn't appreciate it.
So,
where do we start from? So what is quantum mechanics?
What is quantum mechanics? Well, it's the best way we know of today to explain the world, and it's, I think, a pretty wonderful way of thinking about things. And it's kind of an unfair question because there are many good physicists that said over the years that if you really claim to understand it, it means you don't really.
Mm-hmm.
Because to this day, I teach it every semester now, and I'm still every time struggling, even the first lecture, with things that we don't really understand all the way through. But it works, and it can sometimes bother you.
Is it a theory or is it reality?
So quantum mechanics is a set of axioms, or we call them postulates, that every theory that you build and that satisfies those postulates, we will call that a quantum theory. And there are several different theories that describe, for example, how light gets absorbed in materials, right? That a certain quantum theory that requires quantum mechanics to explain it properly. But there are other theories that use quantum mechanics in other areas, like to explain experiments in CERN. Those are high energy particles colliding with one another. That's another type of quantum theory, a more advanced one, that will also go by the same postulates.
Is this a sort of evolution of Einstein's theories, or is it completely irrelevant, or am I just completely revealing my ignorance about everything that has to do with physics? Like, is this somehow related to
Einstein? It is related to Einstein.
Okay.
But when we say Einstein's theory today, we think about gravity normally, about gravitational fields and about how gravity in large scales work. And it is true that around the same years, Einstein also worked on contributions to quantum mechanics that he later came to, let's say, despise or try to modify, try to correct. So quantum mechanics today isn't considered Einstein's theory, even though he contributed to it.
Because one of the things that I always thought I knew about Einstein is something about the way light propagates in waves or particles, or I mean, is that not, that doesn't relate?
It is part of it.
Okay.
The idea that every particle is both, like we think about it in two ways at once, is one of those peculiar things, like it's a particle and a wave, is really, like a large part of it is due to Einstein. There was an experiment called the photoelectric effect, where light got absorbed in some piece of metal and caused electrons to fly out, to get emitted from the metal. And then those electrons were pulled by some field, by some electric pull to them, and then that experiment was really unexplained until Einstein came with a theory that explained light as a particle, which was kind of this back and forth competition of how do we think about light properly. And he helped form how we think about it today, which is as a kind of combined creature that is both a particle and a wave.
And is there a dispute over the quantum mechanics, or like are there scientists who oppose it in any way, or is it in complete consensus?
Well, I would say two levels. It works. Whenever we come to calculate something, it works. Feynman called it shut up and calculate. And that was the theme, the way by which quantum mechanics was applied and still is. Some scientists say that it is incomplete, in a sense that the way we can calculate it, but it doesn't mean we understand things fully. And now, I don't think there is anyone in the mainstream that claim that there is anything wrong in quantum mechanics, but there may be, and that's a debate, and that's interesting, maybe there is something more to discover. Whether we understand everything about it, or there is still something more to find out, that's an interesting question.
But what does it mean, shut up and calculate? Meaning, if you can create some kind of predictive experiment, like you can say, given this will happen, and the calculations work, but we don't necessarily understand why they work?
Yeah, exactly. It's you have a theory to calculate anything that you need, but it doesn't mean you understand it fully. And that's part of what
that's
makes
scary.
it.
How did we arrive at it if we don't understand it? Did someone just be like, you know what, multiply that by 2? Yeah, that should be it. And then it worked.
Right.
Like, oh, wow.
Yeah, there is. I mean, we think about it in what do you need to know? If you know the state of the system right now, you know how to describe the world at this moment. You want to know how it will look like in a couple of seconds, right? This is called the evolution of the quantum state. How to describe how it evolves in time, how the world will look like in a couple of seconds, let's say. And there is a rule for that, but there are kind of two rules for that. There is the rule of how it evolves properly when you don't look at it, and then there is the rule of how it evolves when you do look at it, right? And that's a peculiar thing. Everyone is bringing the Schrödinger cat, right? It's a cat in a box. There is some process inside that may cause the cat to get poisoned and die, and then you don't know whether the process happened or not. It's happening randomly by some quantum process, so it can happen and not happen at the same time, and then the cat is supposedly dead and alive at the same time, and that's what the theory predicts. But then there is another part of the theory, what we call the collapse of the wave function, which is telling you what happens once you look at it. And it's annoying because you should...
But why is our look a factor?
Yeah, that's exactly what bothers people, right? We know when we look, so we can calculate it, right? But it is a factor. And that people would like to have a theory that is in some sense cleaner, maybe more understandable, where you don't need to put us as the observers as part of the theory. And that's, I agree with the general feeling that there could have been a nicer theory, and there are many candidates to that. But today, all of those different candidates, they do not really matter in the sense that they predict something different.
And I have two questions. it's so
Really?
I came up
Only
with
two. Then I got it. I got two questions and then I got it.
I have many questions, but until I say them, do they exist even?
They both exist and don't exist.
Exactly. So first, is there like practical uses? You can give an example in our everyday lives that quantum mechanics affect our lives. And the second, if the rules explain everything in space and time, basically.
So I would say on quantum mechanics matters to us. Does it and where? So it matters to us in many ways today. First, we already live by devices that operate thanks to discoveries that were made in quantum mechanics.
For example,
like silicon that is part of every computer today.
Yeah.
The transistors.
The chips, you mean?
The chips inside actually rely on a lot of complex dynamics of electrons and holes and what happens in transistors, which are all due to the evolution of understanding that started and built on quantum mechanics. And that is today considered an old story, right? It's something that is understood for so long. We today call it kind of quantum 1.0, kind of the first revolution of quantum mechanics from the 20s of the 20th century. And that's many things like that, like LEDs for light, most of lighting today, laser pointers and other lasers that are used for a lot of other applications. All of this, communications.
Is there any chance that you can explain one of those in
for
something
dum-dums?
that we might be able to understand? Like how do the chips or the LEDs, how are they based on?
Some principle that helps in LEDs and many things that involve light are in the end something that have some material that is based on electrons that are held together and make some kind of jump. The jump is something that you get when they actually fall in their energy level and emit a photon. And that translation of energy from electrons to photons, what we call light, is something we can explain because of the rules of quantum mechanics. It's a discrete event where a single electron emits a single photon and loses energy and makes a shift inside a structure that describes this material.
And how did they explain it before, or they didn't? They didn't know the reason, how it works.
I would say LED as a light emitting diode is something that's
new,
more recent.
Yeah.
Today we don't think about it as new. But before that, there were simpler theories for light absorption, for that you could scale things, but not advanced enough to think about devices that are today modern. So in a sense, all of this is quantum mechanics and its contributions to the world that we don't even think about today.
And before we get to your second question, which was about does it explain all things in space and time, you mentioned quantum 1.0. What's quantum 2.0?
So I guess that's the thing that we're more excited talking about today, because something happened that caused quantum to become a topic of discussion, right? We don't even know that we use it for 1.0. So what do I mean by quantum 2.0? Something over the last, let's say, 20, 30 years got us to get interested again in quantum mechanics and rediscover or maybe discover substantial new things about it. And that is what we think about as the second quantum revolution. And it is ideas like entanglement, if you heard this word before, which means that different particles can become connected in even though they are very far apart. So you can connect them in a way that will, and then separate them to, let's say, two different planets, and then apply on one, and it will alter the other right away. So those kinds of connections sounds like
a wormhole.
It sounds like a wormhole, and actually some important people with good ideas tried and still try, some of them, to explain this through wormholes. So maybe, although it's not considered.
So you take two particles, you bind them together, then you separate them, entangle them, then you separate them. But like twins that can always know each other's thoughts, they remain somehow connected, but we don't know why.
Right, and then some people will argue whether we need quantum mechanics to explain how our brain works, or can you explain effects like telepathy and other things with quantum mechanics? It is not
Uri
considered.
Geller.
Yeah, Uri Geller, right? And there were events.
mechanics
There
doesn't
were
explain
events.
that.
So mainstream science doesn't see any reason to believe in telepathy, all right?
Mhm.
And there was, to the best of my knowledge, some research financed trying to check that, and no event or nothing convincing on this. It would be wonderful, right? But it's unlikely that it will be possible or based on quantum mechanics, because even if the particles are connected in some way, they still cannot transfer information, for example, faster than the speed of light, even though they will alter one another. And that's kind of, it feels like a very tough situation to be at. They're connected. You alter one, it changes the other one right away, but you cannot use it to transfer information.
But if you decide that turned on is 1 and turned off is 0, maybe I'm applying for the Schmidt. If you decide that, in theory, you could
You might get $2.50.
you could build a computer maybe that would, you write something in one side of the universe, and
So you cannot. The rules
Okay.
don't allow that.
Yeah.
No, you can
bummer.
cause changes to transfer immediately, but not ones that will transfer information. And it
Mhm.
sounds pretty weird, but
Yeah.
the rules are very precise, and
Okay.
it's really beautiful. Now, but still, you can use them for different things.
Uh-huh.
Like when people talk today about quantum communications, for example, there are already satellites that are actually using quantum communication to secure information transfer in a way that will not be possible to crack by classical means.
Mhm.
Not using entanglement, but using other.
They use entanglement for that. So there are
Already.
applications that are relying on entanglement already.
Hmm.
You can argue whether
Wow.
how important they are, but there are Chinese satellites and communication channels relying on that. So entanglement is in use already. And when you
Wow.
think about a quantum computer, which is the
Yeah.
biggest hype and buzzword now, they also rely on entanglement, and it's a critical aspect of it. So yeah, there is
Wow.
a substantial use of entanglement now in more and more types of applications. And I think that's one of the things that got people to get attracted back into this field and really invent new things.
And the major breakthrough, if I understand correctly, is just the speed of computational power and the speed of communication, like the right, or is it more than that?
It's not exactly the speed. No, it's
Complexity.
there is something about the complexity or this space you can really check. Like a quantum computer has this weird property that you can check. You can run the same algorithm on every possible input at the same time, right? If you want to have let's say you have a
Isn't that speed though? Because you could have technically done it by doing one and then the next, but it would have taken eternity. And now you can do them all at once.
So you can say speed in the sense
It's
that
space, but
like
space
volume.
affects
Yeah.
speed.
Okay.
Yeah. Now, it's not as simple and as amazing as it sounds. Yes, you can cause the quantum computer to run on every picture of a cat or a dog online at once to try to find out whether it's a cat or a dog, right? That's an important thing to do, I guess.
To find the perfect TikTok video.
But the computer will actually execute it on every picture at once, but it will not tell you. Getting the output out of that computer is really tough, and that's why quantum computers are still quite limited in what they can actually promise us. And
So it'll get the answer, but it's like I'm not gonna share it with you. I don't want to tell you.
That's a
It's
kind
like, do you know the answer? I don't know.
it is hidden in the quantum state, but it's not necessarily that simple to extract it from the quantum state. So the algorithms we know how to make are the ones that are actually in very specific cases where we know how to extract useful information out of the quantum state.
And those rules, again, to my question, they apply everywhere in the known universe, as far as we're concerned?
Yeah, so if back to space and time with quantum mechanics, to the best of our knowledge, they apply everywhere, yes.
So they started with the universe, basically.
Yeah, that's how we understand things today, yes. And even when we argue about like different theories that are still missing, right, there are things we don't know how to explain, like dark matter and dark energy, things of that type that we don't know how to explain. Every rule people try to develop will almost always will be still abiding the postulates of quantum mechanics, because we trust it that much. And it's an interesting thing. And there are some efforts to try to develop other variants of it.
Yeah. Wow.
There's something like religious about it, right? Like Na'aseh v'nishma, we will do and we will listen, right? They say about the God's commandments to the people that like You don't need to understand it. Just shut up and calculate.
Yeah, you can say that. You know, it's an interesting story that for many years after the Second World War, it was quantum mechanics became a kind of standard tool, and that's all. And then the idea is that let's try to doubt it, like let's try to modify it, became a kind of not mainstream, not needed, looked down upon. And still in some places, and Israel was one of them, there were substantial research centers trying to challenge the main theory of quantum mechanics, find alternatives, like Yakir Aharonov from Tel Aviv University, or Lev Weidman, also from Tel Aviv University, are examples of researchers that worked on the foundations of quantum mechanics, even in years where it was not as mainstream as it became today because of entanglement and quantum computers. And it's an interesting thing that Israel always held this beacon of let's challenge it. Today, it's a much more mainstream thing to work in those areas.
So what's the big things we're oblivious about?
Oblivious about, you mean in the
like
context
we don't
of,
the big things we really don't know
in a context of you mean wider effort
in physics? Yeah.
it's a big. What are the most important open questions in physics, right?
Yeah.
Well, so now every person will come from his or her field and say, okay, this is the most important one in a
politics. You say there's politics.
I think there are accepted problems like dark energy and dark mass, but also like superconductivity. Here is an interesting challenge that is closer to technology. Superconductors today are used in MRI machines, but superconductors today also thought about as part of the backbone of train transportation. If we want to get trains levitate on magnetic fields, so you can get less friction and have faster trains.
Like the Shenzhen, like the bullet trains in Japan.
Now, when you want to have a very strong magnetic field there, or for MRI machines, it's critical. You at some point run into a problem that you cannot put that much current that creates the magnetic field, the electric current, into the system before it heats up. So you want to use a superconductor to keep it not heating up that much, to lower resistivity, or in the future maybe to even build complicated electric circuits and lower the loss because of resistivity in the entire electric grid. And superconductors would be amazing for that, but today they only work when the system is really cooled down to super low temperatures. And some years ago, there was this really amazing discovery that some certain very unusual superconductors still operate at relatively high temperatures, which is potentially important, especially if we find a way to push them up even further to our temperatures, room temperature, right? So you don't need to cool anything down. No one so far has a superconductor that can operate in normal conditions, but I'm trying to understand how they operate, understanding the microscopic, on the atomic level, what happens there, what causes them to work, is really important because it will allow us to open a lot of areas of technology.
So we use it, but we don't know how it works?
Yeah, in some places we use high DC superconductors, high temperature superconductors that are without knowing exactly how they work. Yeah.
What?
That's really cool, right? That's one of those things. Physics allows that to happen.
There was someone that used to work at Intel told me that they have lasers that create these ridges in the silicon that are so small that there's no microscope on Earth. It just kind of reminded me of it. There's no microscope on Earth that can see and check if if they did it right. They do it because it's like.
So actually, that's an interesting challenge for my lab, because we develop high-end microscopy, and the best ones will not be optical microscopes. They will not rely on light. They will be electron microscopes. Right, the electron microscopes can look at that. I bet they can. And Intel has a group, even in Haifa, that is looking into that area.
Was it true that at a given point in time they were making etches in silicon that
were very hard to look into? But I think that if they really wanted, they could have come to the Technion. We have an amazing microscopy center, and there is always a microscope.
I'm going to go back to this guy and be like,
I want my money back. but the output of your microscope, how does it looks? But it looks like a regular output of a microscope. But the way to achieve it is with
electrons instead of light. Yes.
How does it work?
That's there are generally two ways to use electrons to look into materials. One of them is called the scanning electron microscope, where you bring a beam of electrons that is focused to a tight point, and then you scan over point by point, like the old TV screens. They were scanning with an electron beam actually on the screen to create an image very quickly, so it looks like it's a permanent image. So it's a scanning point by point, and then electrons scatter, and you collect them. And by how much of that scattered and how much the detector gets, you get how much the color of each point. And it's a kind of black and white, but still gives you a very high resolution image. And then there is the even higher resolution microscopes called the transmission electron microscopes. Those rely on the electron beam becoming a wave. You span it, so each electron is a wide wave. It can be tens of microns, which is millionths of a meter. So it's relatively large electron beam. And then it goes through the sample you want to look at. And what you look at the camera is underneath. So you actually look at a kind of shadow of this thing you want to look at. What electrons penetrated and what didn't.
But we can't
like
see...
a silhouette.
We can't see atoms. We can.
Here's a good challenge. What's the smallest we can see with an electron microscope? It is getting better every year, and atoms are already within range. We even see smaller than atoms. We see distances between atoms, and in recent years, you can ask what's connecting the atoms.
Right.
Those are electrons that fly around and tie and bind the atoms together. We can see even the shape of the electron cloud that connect atoms. So yes, we can.
And
That's
didn't
mad.
Yeah.
That is just mad.
No, it's like you can get mad from, you can. How can you sleep at night after?
Because you can keep getting smaller.
So what's the smallest we could see?
You can look at
Didn't they
the challenge,
discover
right?
that atoms are actually, there's something smaller, there's a name?
Yeah.
Quarks or
Quarks.
whatever.
Our first protons and neutrons building the atom, and then you can build a proton and a neutron from quarks. Yes, that's so a microscope that can look into the nuclei that is still beyond reach, but is something that
Within your lifetime.
people are thinking about, and there are ways to get smaller and smaller. But I like another dimension actually.
Okay.
Because we're always thinking about what's the smallest we can see in space, but what's the fastest we can see in time? What's the shortest, like the fastest movie you can make, right? Because electrons.
You gotta have to rewind and explain that. What do you
Right,
mean?
because
what's the
we're looking at
fastest
atoms, right, and
Yeah.
we see how they are arranged and structured. But now imagine that something is happening there.
FPS. What's the FPS?
Yeah, what's the
essentially?
FPS, right?
Yeah.
How fast? Okay, so now you put current on the atom. Let's say we have a lithium battery, right? Lithium-ion battery there is something happening when we operate our smartphone, right? And the battery runs out gradually.
Mhm.
So something moves inside. We want to see the motion of that something, so we can design a better battery. Right? The motion matters, right? Or when light gets absorbed into a plant and creates energy for that plant, photosynthesis. Well, something is happening there. How quickly does it happen? Or when we
Right, because basically FPS is frames per second. So our eye at, I don't know, it's like, I guess
48 or whatever, 24.
you can still tell the difference between like 120 hertz phones now are a thing, right? Beyond 120,
it's too hard to see.
you won't notice the difference. But motion has endless, I guess, frames per
Right.
second.
So imagine
Right.
they have there is a bullet that is hitting some apple, and that breaks
Right.
to pieces. There are movies like this online,
Right.
but you cannot see it with your eye. But you can have a really fast camera.
Yeah, you have cinema cameras that do I don't know, 1,000 frames per second. Or
You can even get to a
whatever,
million frames per second if you want to see something super fast, like a bullet hitting an apple and breaking it to pieces. But so that will be a million frames per second, and will be sufficient you'll slow it down, and you'll see a movie in slow motion. And but that's still, millions frames per second.
It's not enough.
It's not enough for us. We do way more than that.
Because a second has endless milli or microseconds or whatever
Right.
inside it, right?
Right.
Basically.
So a rate which we will call a millionth frame per second means we are looking into the microsecond, 1 millionth of a second as our frame rate. But that's still pretty
Not
slow
enough.
for if you want to see things like electrons flowing in materials, right? What will be the rate of electrons flowing in materials? So a millionth of a second will be a good time scale for effects like electrons flowing.
So it's a millionth in the square of, I'm not a mathematician.
Right, a millions times a million, or what we call what's the 10 to the 12, the tera, right? The giga is the is the billion, so that one after is the tera.
Right.
like when we say terabyte.
So that's the goal. We're not there yet.
Well, depends. So if you want to look at how light flows, that's even faster. Then we care about resolution on the scale that is 1,000 times faster than that. So 1,000,000 times 1,000,000 times 1,000, and we're doing that.
Oh, what's 1,000
And now
more?
we're developing another 1,000 after that. So we'll have million, right? And that scale lets you see things like, for example, light motion, how light flows inside the tiny elements.
Space.
How light flows inside tiny elements. We do that. And
That's incredible.
So,
And what do we deduce from it? Nothing. It just looks really cool. We drink
The
champagne.
perfect TikTok video.
I imagine. I imagine like there's a
one,
cinema. There's a nerdy cinema in the Technion where all the nerds come and they just eat popcorn and watch light in 1 million.
They're like, that was so worth that 2.5 million. Thank you, Eric.
So seeing things that are super fast is curiosity is legit, is important, right? It pushes you to things you didn't think about. So, for example, we were doing this interesting experiment to try to create.
But if you think that's fast,
right.
It's nothing like watching Ethan eating a burger. That's like the fastest scale. Sorry, go on.
No, but I mean, we are looking into things that are super fast, and then it causes us to realize things you didn't expect.
Okay.
Like to improve, to develop new technology. Like we have patents that appeared because of basically mistakes in the lab, where we tried to image things. Like there is something called terahertz fields. Terahertz field is an area of light that is not radio waves and it's not visible light. It's not infrared. It's somewhere in between that is relatively unexplored and has enormous potential. Like to look into the human body, to do security scanners that are better and more efficient and not dangerous. There are reasons to develop that area of technology, and we worked for that. We tried to find an electron microscope technique that will enable us to image how terahertz field evolve, and that's super fast. And then we found that it actually acts back on the electron and improves the electron microscope. So now we can imagine to improve the technology of electron microscopes because of an experiment. So those are the kind of things that you can never plan. And I think that's...
So maybe let's get
to the 2.5 million. So you first of all, tell us maybe how you found out about the 2.5 million and what was your reaction? Did you
listened to our episode from last year with with Oded,
yeah,
with the Chavi.
I
and he was like,
with him on this.
No, but I meant, how did you find out that you were awarded?
Okay.
Well, okay. Actually, it's an interesting thing because it comes in an email. The Schmidt,
the spam,
because it's Google. It's Google.
Yeah.
It's 2.5 million. They're like, just send him an email.
Hey, it's Eric Schmidt spam.
It's actually amazing how this thing works, because it's not like any grant I ever saw. It really is. They basically go and ask for applicants from every big university on earth. And still they somehow, and then they run this super complex process of filtering people out, where they ask for many recommendation letters and advice from experts, and something larger than anything I saw. And still eventually it's an email, right? It's an interesting thing, right? Because they run this kind of super open-ended, and their thing is that it's completely flexible. Right, they ask you to. The only rule for submission is that you cannot be on things you're an expert at. Like I couldn't write about quantum or about microscopy.
All the things we just discussed were out of
scope for the application. You have to show that you can suggest something wild, ambitious.
So what did you suggest?
And I suggested developing algorithms, artificial intelligence algorithms, to try to help us find what directions of research are worthy and will be the most important and worth pursuing.
Wow.
in a wide sense, and also focusing on fundamental physics and mathematics, but asking algorithms to help us do that. And I think this is it's not a very standard thing to do. Maybe that's part of what got them interested. And there are reasons why this is exciting. I mean, we want to have a computer that will tell us, that's the best direction to go at, right? That's what we should try.
Is it doable though?
In some proof of concepts, yeah, I think so.
How would you approach building such AI?
So I generally would like to have that AI for anything in life, right? who will be my forever after?
Shall I date?
Well, my wife likes to say that whatever she recommends, I do the opposite.
Yeah.
So maybe
That's a good algorithm.
She's an anti-supercomputer.
So yeah, so maybe I would love to have this, but I think she would think that if I had this, I would just choose whatever it recommended. I would choose the opposite.
We need to be kind of humble and just recall that we already have algorithms like that.
Yeah.
We don't drive on a highway today at least traffic hours
Sure.
without asking for an algorithm to tell us where to go.
Yeah.
Right. And there are many things like that. Like we are quite happy with the Google results, which is based on the heavy AI when we search things online.
But what does it? Because and jokes aside, I really do sometimes. What drives me, I'm sure subconsciously, is like I don't want to be told what to do, and I think every taxi driver is a testament to the fact that like there's something in the human spirit that wants to make those decisions on their own, right? You get into a taxi in
Even if
Israel,
you fail
and they
miserably.
refuse to put Waze, and you're like, why aren't you putting Waze? And the taxi driver's like, no, don't worry, I know, and then you get stuck in traffic.
Yep.
So what does it mean for us as humans? Like we're not going to be able to make decisions anymore.
To a point where you will be, because you can always decide to refuse, right? Not to follow the advice of the AI. You can always do that, but it feels a bit funny to go against the recommendation which you learn to trust. This is why we trust Waze. What does it mean to us? We like to have Waze, right? We like to have it also recommending directions to pursue, or what's the best product to buy. That will be excellent if we really trust an algorithm doing that, right? So why not in bigger and more complicated questions? Like what is the right direction to invest money in when we want to think about the right direction to, help cure cancer or fight global warming? We would like to have an algorithm to tell us those things as well, right? And it's just that no one knows how to do that in full. But then in some areas, like in mathematics, in physics, the rules of the game are more clear. And I think that there you could develop an algorithm like that. It's not easy, but it's more feasible. And we tried some of that. In mathematics, in areas that relate to mathematical constants, there are formulas that give you constants, famous ones like pi, right? Like the golden ratio. There are other famous constants like Feigenbaum constant and Euler's constant. Those are famous numbers that are important in mathematics, and we asked an algorithm to help us find formulas for them. And that's something we can do. This is something we already showed possible. So this gave us confidence that we can take this into new areas. And then if you think about it bigger, we would like to have an algorithm helping us do research, tell us what direction to follow. So in some places that may be possible, or at least as a tool to help you. You can always decide to ignore it, right?
But how do you, I'm assuming you have to train it with data from the past. You train it with past data, and then you give it a goal and you give it some constraints. Like the goal would be truth, right?
Right. That's right. So
isn't that
in mathematics, the goal will be truth and finding a formula that is satisfied, and the data will be, in our case, it's really the digits. If you think about pi, right? The digits of pi. Is it a random set of digits, or is it something very ordered? Is there a rule for telling you what's the next digit of pi? People tend to say that it's randomic, but it's actually not, because we know how to calculate it. So there is a formula for pi already. Otherwise, we wouldn't be able to calculate billions of digits of it. So there is data. That's the basic data. And unlike every other area, probably, in machine learning and in AI, this data is clean. We call it ground truth. Right? It's a clean set of data that we can rely on when we build algorithms. And that's, in a sense, making it somewhat different from other areas of research in this field. So yeah, we have the data, and it's quite clean.
And then eventually onto less structured data like medical research and things like that. You think that it could be applied in those fields eventually?
Yeah, and in some ways it is already attempted in different places. Like people take data from bio information in different places where you'd have a gazillion, tons of data that you can try to search, not just for something you asked, but try to develop an algorithm that finds some rules, some repetitions, some patterns. And those patterns can help you identify a direction to study. So this is the kind of thing that we are starting to ask AI to do for us.
So how do you use the money to, because I guess since you don't deal with those things, your lab isn't trained to,
So
create AI. So you basically use the money to hire talent to help you accomplish those goals.
Yeah, it's mostly
Like
hire
you
talent.
use 100K and the rest you pocket. No, I'm just
You
kidding.
cannot, yeah.
Yeah.
It's only for research, and but in many ways it's like a startup company that relies heavily on salaries as the main thing. Yeah, they hire talent, and in a sense, I like the way physics works in this, because physics, the lab, it gives us kind of a place to collect creativity around it.
Mm-hmm.
It helps you in two ways. One is that it gives you experimental results. It means nature can surprise you, and there is like surprise you. It forces you to be more creative, to get things that you will never get on your own computer or piece of paper or with a pen. It forces you to be more creative because it gives experimental results that you couldn't expect.
Yeah,
and that drives creativity. But it also makes a group form around. The lab is like a place for people to exchange ideas, to fight and argue about them, in Israel especially. So we have this culture that is really open. And when I go into mathematics and play with AI in this, I try to work the same way. We bring really amazing students working with us, and also people like with PhDs or people from the industry that are just interested in this, and we form this community. The project we started around this, that runs now for a few years, is called the Ramanujan machine. Ramanujan was an Indian mathematician that was famous for his untraditional approach to mathematics. He was the one that didn't learn in any formal system. And then he had to reinvent a lot of things. And when he came to make discoveries, he made them without providing proofs. So he was considered kind of an outsider for the math community for many years. But then when he made those discoveries, still to this day, people follow and try to prove things that he came up with. And I think this is one of those wonderful things that are outside of academia that can be substantial. So the Ramanujan machine is our kind of attempt to bring a computer to be our experimental lab in mathematics, to surprise us with results that we didn't expect. And that's the kind of thing that we work around. We develop algorithms to bring us surprising results, and then they drive our research. They drive our directions of research. So that's
and how long has the lab existed now? Like, when was the award? The award was granted now.
Yeah,
so
the award
you
was granted now.
So you're just building the lab now, and you guys are going to continue the work on this Ramanujan. That's what
Ramanujan.
Ramanujan.
Yeah.
Ramanujan.
Ramanujan is so when you say the lab, so our electron microscopy lab and X-ray lab, which we can discuss, the labs that are, let's call them physics oriented, are running since 2018, and evolving. Our X-ray lab is more recent. The Ramanujan machine project is more it ran in parallel, but it was not around a real lab. Right. The biggest thing there that you can call a lab is that there is now an algorithm that runs online. Everyone can download and contribute. People run it on their own computers, and it's like mining for bitcoins, I guess. They mine for mathematical formulas, and bring us formulas to, like, they help discover formulas. So this is a community that provides those surprises for us, but it's not a real lab that built in a special location.
But this is where you're going to invest the $2.5 million, the Ramanujan?
Around the Ramanujan machine, part of it, but also in taking those ideas outside of mathematics. We go for physics, for fundamental questions in physics, in trying to combine quantum mechanics with other fields. Like there are big open questions about how to combine quantum mechanics with gravity, like the two areas that Einstein worked on, if you like, and never worked together to this day, is one of those amazing problems that it's maybe considered the most important problem in physics, and still applying AI in that area is relatively a young field.
Can you explain why it's the biggest problem?
In some sense, you want to combine all laws of physics to a single unified theory that will mean that you really understand things.
The theory of everything.
Yeah, the theory of everything is right. And Einstein was saying, or at least quoted for saying, who knows if he really said that he wants a theory that you can put on a T-shirt, right? That could be nice.
Explain.
Something short and powerful.
Mm-hmm.
So a theory that combines today quantum mechanics and gravity, that the two, it doesn't work. It doesn't combine well.
Mm-hmm.
And that's
so
a
we
big
can't use quantum mechanics to explain gravity.
No, we don't know.
The way we explain gravity, can we explain gravity?
We
today?
have a theory of gravity, and this is the thing that's attributed to Einstein.
But it doesn't correlate with
No.
quantum mechanics.
And how to combine them is a good goal. Whether AI can do it, well, that's a tough, it's a big, challenging, crazy question. But there are things that happened in recent years. In the last about year and a half, there were 3 groups around the world that contributed with papers that automate some of the machinery that's needed to ask those questions. So,
but I'm trying. So is quantum mechanics not good enough to explain the observations that we have around gravity? Meaning, before I thought we said that quantum mechanics explains everything. So can't we just throw gravity out the window and say quantum mechanics it is?
well, quantum mechanics it is for everything we try to use it for, and then we suddenly try to explain how GPS works, and we need to explain the small time dilations of the satellites that are part of the GPS system, and there is an effect there that requires gravity, and we don't know how to use quantum mechanics to do the same thing, like to build gravity from quantum mechanics. You can imagine something like that. So people try that. They also try to just combine them in some legitimate way, but then they get and we get contradictions.
Okay,
and that's,
but there
that's
is there are holes in quantum mechanics. Then there
are holes
things
in our understanding of nature.
Yeah,
right. It's not like if you take quantum mechanics as is, it's good for wherever it extends, and there are no contradictions there. But once you try to combine it with other things that are not compatible with it, then it fails.
Meaning right? There are phenomena that exist in the universe that are not explainable through quantum mechanics, like this, for example. I'm not exactly sure what you said. Satellites sending something, the message is getting scrammed.
We can think a bit about how GPS works, but
the latency you were saying.
In Quake, it's a satellite, and there is some latency, and they collect some signals
and
from several of them.
That isn't explainable through quantum mechanics.
No, not the quantum mechanics alone. So it's not a kind of thing that explain all. Right,
I see.
And science is not like that normally. But finding a unified theory that would be able to explain all would be wonderful. We are not really close to that.
So is it too late for us to study physics and join the team?
That's for the Ramanujan machine project. I think you could. I mean, there are ways to contribute to it by running it on your computer. But if you want to play more, then like develop algorithms.
Let's say if you ask the algorithm that's supposed to give you recommendations, it would say there is absolutely no universe in which either of you could be contributing to this project in a positive way.
People because this project has some visibility, people contribute to it from many different countries. Write online, suggest, run the algorithms, find out things, and not all of them have the most traditional university education necessarily. Or so there are ways. Yes, I would say that it's not hard. It's not easy, but yeah.
Okay. He's like an answer of a politician.
Yeah.
Yes, of course.
Yeah.
Anyone can join. You can join.
We should get more what do you think about that? That's a good last question. Should there be more physicists in politics? No.
I don't know.
I thought you were going to ask.
My dad's a mathematician, and he always complained about how much politics there is in academia. So I feel like maybe academics could make good politicians. No.
Why the debates are so fierce.
Yeah,
because the stakes are so low.
No, but in the actual, like in the academia, like in the who chairs the boards and who sits in different, who gets tenure, who forms the labs, who gets this, who gets that. Like there is so much politics now.
I guess there is politics.
Does it get in the way of the science?
There is politics everywhere, and it could. I really like Israel in that sense. That I got back from MIT. For a faculty position in Technion, and partially because people really care. You know that you can take risks, and someone will have your back. So yeah, I guess there is politics everywhere.
Also, when you
can do more with the politics we have here than in most other places.
When you're 2 meters high and you have the body of Arnold Schwarzenegger, who would tell you no? That's also
In academia, I don't think it matters that much.
No.
If you come with a crazy idea, with crazy vision, and an idea how to do it, then some people will follow. Yeah, that's what makes it so fun.
I was thinking Eitan's last question would be, do we need more physics students?
Well, generally, I think everyone thinks about computer science these days because it feels so, and still you will find that many of the people that started big companies and made substantial contributions came with the physics understanding and still learned how to do the stuff needed in computer science. So it's a very useful direction of education to come with, and with things that are now happening, like quantum computers becoming more substantial into technology gradually, we'll need more physics education. Yeah, and that's
wow. I mean,
I think that there is a way to think about it we think about labs and we try to imitate it with computer algorithms, but in the end, having experimental labs that are powerful is a way to create new ideas, to innovate. I think it's a powerful trigger for like ideas, testing ideas. And the fact that, like, for me personally, the fact that Technion invested in me as in my lab, in building a very unusual experimental setup that was expensive and complicated to build, it allows a lot of things. It creates a lot of ideas. It's really becoming a center for innovation, for patents, for things like that. And that's one thing that wasn't that trivial in Israel to do that in the past. We had always those debates on, can we do experiments abroad? Why invest so much money in doing it in Israel, where we can just fly out and do the same experiment in a lab built in Germany or the US? Why do it here? And why not just pay for the flight ticket? It's way less, not as much money.
It's cheaper to do it there.
And I think COVID made us realize that there is an importance to have this stuff here, right? And also it makes ideas happen. So we are thinking now about what will be the future dream labs that will be kind of the big facilities abroad, but on the Israeli scale, more modular, faster, more flexible. It will be places for ideas to form. And I think we need physics for that as well, because it drives more ideas in other areas of science, in other areas of engineering and technology.
Professor Ido Kaminer, thank you so much for coming. It was really inspiring and mind-boggling. Really? I have a lot of food for thought. You're on social media?
You can look us up. You can look up our lab. Our lab is AdQuanta, and we publish things. We advertise some of the work we do as science work.
So the handle is at
AdQuanta is AdQuanta. Okay.
And that's the website. There's a website. There's a Twitter account. Like, what do you guys?
We have the group website is for the to see who the students are, the real people that do the work, to see what papers we published, what talks we gave, and you can see online. And recently there is also a Twitter and LinkedIn that my group started to write more about what we actually do. So you can follow us there. And also I'm happy to have people coming with crazy ideas and creating interesting collaborations. We have people working with us from all over the world, and it's what's fun about academia.
That's awesome.
That's awesome. Amazing. Thank you so much for coming. Really appreciate it, and good luck in the initiative. Guys, if you like what we do, please support us. Go to patreon.com/2njb and join the club.
Yeah. Be Eric Schmidt.
Yeah. And rate us on Spotify. Give us 5 stars.
Yeah,
or 1 star if you think we suck. And that is it.
Thank you, Professor.
Thank you so much.
Thanks, guys.
Bye.
Guys.